of however big a matrix you have to diagonalize, you know, n by n matrix, depending on how many energy levels are degenerate. And so if it was like 3, you'd have to precisely diagonalize a 3 by 3 matrix, and so on and so forth. And so, but the idea, I think it was that, now here I think that what they did is maybe they had it where 2 of these guys were the same, and then there was one that was different right here. So it'd only be, in that case, it's not so bad. It'd be a 2 by 2 matrix. And so the idea is, okay, you diagonalize this piece of your thing right there. And by the way, this is another thing that I may avoid. It's this thing where you're actually using, they call it unitary transformations, where you're actually taking your Hamiltonian, you're doing a unitary transformation. And it's kind of conceptually, it's just a, sometimes it's not that easy to wrap your mind around this whole process. And so I'm going to leave that for later, if at all, just because sometimes I think it gets really confusing to get into that. But at any rate, the bottom line is that, okay, they essentially, notice that this results right here, if you look at this, looks pretty darn similar to something that I had in my notes before when we diagonalized the 2 by 2 matrix before. So it looks almost exactly the same, I think. And so the idea is, okay, you basically diagonalize whatever size matrix is needed to get rid of, because the idea is that, okay, hopefully when you put in these off-diagonal terms and then you diagonalize it, it breaks the degeneracy. And so the idea is that, because you have a plus or minus, and then if this is non-zero, you'll have one energy level that's shifted up a little bit from the original one, and another one that's shifted down a little bit from whatever the original one was as well. So like in the case of the hydrogen atom, there'll be a number of things that are going to split those levels, like spin-orbit coupling, for example. There'll be some things where you throw in these extra corrections, and so then they're no longer perfectly degenerate. It's not that easy to see in spectroscopy. You have to do like really, really careful, precise spectroscopy to be able to see the splitting. It's a little easier if one applies a big magnetic field, because then the splitting becomes proportional to your applied field because of the spin of the electrons. And so then you can actually see, okay, yeah, I can actually split out those different, what were formerly nearly degenerate energy levels in the case of the, let's say, the electron in the hydrogen atom. So
whenever you find the characteristic equation and you find the eigenvalues that split the equation that you're dealing with, you normally have, in math we have to determine which set we're dealing with. Do we care about if it's complex eigenvalues, real values?
Well, okay, so
where does that come into play?
So here, as long as we're talking about energies, these are always going to be real. So, however, these off-diagonal matrix elements in general will be complex.
Yeah.
They will have the property, because this is Hermitian, that this guy is, or this guy is the complex conjugate of this guy right here. So that's one of the, again, I just want to remind you about. This guy, similarly, will be the complex conjugate of this guy right here. So that's one of the properties that I think is handy to remember regarding Hermitian matrices or Hermitian operators. And so if you see when you're going through your algebra that your matrix doesn't have that property, okay, and it's supposed to be something like energy or Hamiltonian, then okay, something's wrong. Okay, I did something wrong in my algebra. All the diagonal elements should be real in that case. Oh, and then, okay, then the idea is that if you've taken a piece of this, of your guy, you've diagonalized a portion of it, you kind of put everything back in, so you have, then the idea is that, okay, one could then, if you still had some other, let's say, off-diagonal elements somewhere else, you could then just use regular perturbation theory, as we did before, would be the idea that you had a more complicated thing, where parts of it were degenerate, and maybe parts of it were not degenerate. This gets to be, I don't even know if I want to get into all this right here. Okay, let's see, I hope there's something, I'm hoping there's going to be something that's going to have some intuitive, that basically to make a little bit of intuitive sense. In the case of the hydrogen atom, Let me just, hand waving. In the hydrogen atom, there's some things that are going to cause these, because remember the original hydrogen atom for the Schrodinger equation, we just said, okay, the various angular momentum orbitals appear to be degenerate to lowest order. Things that are going to break the degeneracy are, one of them is called spin-orbit coupling. The idea is that, okay, the electron, the spin of the electron can couple to just the fact that you have a bit of a magnetic field that's created by the orbital motion of the electron. So that's called spin-orbit coupling. So that's one of the things that breaks the degeneracy of the electron. If we just kind of ignore some of the nasty algebra right here. And so I think in your Thornton and Rex books, I think they may even mention, and there's another thing called the hyperfine splitting and so forth, hyperfine interactions, lifting degeneracy by a magnetic field. So the idea, okay, if you had a magnetic field present and you're coupling, so you have any kind of, in this case, magnetic moment that can couple to the magnetic field, and that would give you something that could act as a perturbing Hamiltonian. So for example, instead of L, it could, well, you could actually, even the orbital actually will give you something, but the spin as well will couple to a magnetic field. And so that's another way in which you actually literally do break the degeneracy sometimes in a way that's actually very useful. So as an example, in let's say NMR and MRI, in that case, actually we're not even doing it for the electron, but we're actually doing it for the nucleus itself. In this case, the proton. If we're talking about just regular proton MRI, and so the idea then is that when you apply a magnetic field, a spin up coupling to a magnetic field, let's say going in the z direction, is going to have a different energy than something with a spin down coupling to the same field. And then the idea is that the bigger B is, the greater the splitting between those two energies. And the other nice thing about, I guess, MRI and NMR is that this proton is actually has a fairly, in other words, apparently the lifetime of these states are actually quite long, and so it actually gives you very sharp spectra. So that's one of the reasons why MRI works as well as it does. It actually doesn't have a lot of things that mess up your image, it turns out. Okay, there are things that are going to kind of have some interesting effects in a way that can actually be interpreted, but for the most part, what they do then, for example, MRIs, they're applying magnetic field gradients, and so that means that you're causing the splitting to change as a function of x, y, and z, depending on how your gradient fields are applied. And so what you're doing is you're actually converting a spectrum into an image, effectively, when they do MRI. Now, ESR, which is electron spin resonance, is where you're looking at splitting involving any unpaired electrons in your system. So like if you have a hydrogen atom which has unpaired electrons, you could do, in principle, ESR. Now those tend to couple much more strongly to the environment, and so there are a few people at the research level that have done ESR imaging, but it's not nearly as clean as MRI. So in other words, they tend to be much more washed out and fuzzy, just because there's so many environmental interactions and so forth. Now there, it's probably closer to what we would think of as regular normal perturbation, in the sense that for ESR, you'd start out with your original electron energy level, for example, and now we apply the magnetic field, and so then that kind of gives you a relatively clean addition, perturbing term in your Hamiltonian, where you'd say, okay, I'm coupling the magnetic, in that case, instead of the LZ, it'd be the spin operator, I guess I'd go in here. But the idea is that, okay, that guy, the magnetic moment of the electron is coupling to the magnetic field and then giving me this extra term, which can then have an influence and actually split the energy levels. And because, and of course, again, the other thing I want to really emphasize, because this is a knob that you actually directly turn, so you actually control the magnitude of that magnetic field. And so then therefore you can control what that splitting is, and that splitting will correspond to a frequency. So for example, at NMR or MRI, if I remember correctly, a magnetic field of 2 Tesla, for the case of proton NMR, corresponds to a frequency of something like 84, 85 megahertz. Whereas if we go to ESR, for the case of the electron, it turns out that even if you go down to a smaller field, like some fraction of a Tesla, you're already pushing the frequency up to several gigahertz in that range. So it's actually a much bigger frequency factor that goes into play for the electron. And I don't know if that's because of that factor of M being smaller, and then perhaps the G factor also being different as well. But, you know, certainly the factor of M is going to be 1,800 times smaller for the electron than it is for the proton in that case. Okay, so that sort of covers those. What if there's... Okay, I think, yeah, this is probably, I know that we're a little bit ahead of, I mean, we're sort of early, but this is probably enough to kind of give you something to chew on, I think, for a while. So what I plan to do then is I will start typing up some homework problems. Some of them are probably going to be along these lines. There's probably going to be one or two that's going to be similar to that example for the harmonic oscillator, involving just trying to use, okay, so let's see, how do you plug in some of the expressions for, I'll just do non-degenerate perturbation theory. I might pull, if you want to start taking a look at, I think it's chapter 9, and I might actually start going in a little bit of the material in Thornton and Rex, because they have a nice chapter that actually goes into, gives you a little bit of the basics about what happens, where does band structure come into play, like for semiconductors, for example. And so there is, I think it's in chapter 9 or either 9 or 10, where they talk a little bit about semiconductors. And so I may actually start going into some of the Thornton material, just so you have a little bit more in terms of real world problems that you can take a look at. And so I may pull off one or two of those as well to go into the homework set. And so other than that, I guess I hope everybody has a good weekend.